Hello everyone, I'm Hawwooi, and the topic that I'm going to say is on reducing unbalanced magnetic pull through active control. And first of all, I would like to say about the background of the research is the reason that I'm doing this research because the reliability of the generator is become more and more important, especially for offshore renewable energy generator, because as we know, the downtime of an offshore energy generator will be quite long, and this will cause a huge revenue loss. So the bearing failure is the main failure of the renewable energy generator, and the unbalanced magnetic pull is the main contributing factor towards the failure. So the machine that I'm looking for the unbalanced magnetic pull is on induction machine. The reason that I choose induction machine is because induction machine is the most robust machine, and induction machine doesn't need any rare earth material to build it. Okay, the unbalanced magnetic pull is caused by the eccentricity of the rotor, which the rotor is misplaced from the center of the stator ball. And there's two types of eccentricity that will happen when first is called the static eccentricity, which the rotor rotates at its own axis but not at the center of the stator ball. And the second one is dynamic eccentricity, which the rotor rotates at the stator axis but not at its own axis. And of course, both of these can be occur together, which we call it as mixed eccentricity. And when there is eccentricity, the air gap length will be different around the air gap. So from the first equation show that the calculation of length difference around the rotor position, and as we know, the air gap length is directly proportional to the magnetic reluctance. So when the magnetic motive force is constant and there is more magnetic reluctance, means that there's lesser flux will be flowing through. So from this we can calculate the air gap flux around the rotor around the rotor. And the method that we use is we compare the concentric rotor and the eccentric rotor and times by the ratio between them, and this, after the derivation, we can get there's additional pole pair plus 1 and pole pair minus 1 will be occurred in the air gap, and this will cause the unbalanced magnetic force. And after that, we apply Maxwell tensor stress on the rotor at each position and integrate it, and this will give us our final unbalanced magnetic pull. And from here we can see that there is a constant component and a 2 times frequency component of the unbalanced magnetic force. So for the constant component, which is caused by the forward rotating flux of the machine, and for the 2 times frequency component is caused by the backward rotating flux. And backward rotating flux will normally not happen in a series connected circuit, so 2 times frequency component will normally be there if there is if every circuit is series connected. And before we go into the UMP talk, the UMP of before we go into the result, we will take a brief look through on the torque slip characteristic of a typical induction machine, which 1 is a standstill position of the rotor and 0 is the synchronous, when the rotor rotates at synchronous speed. So during there is the region we call high slip region, is there's a lot of leakage flux in the leakage flux is the dominant flux, so that means that there's a lot of harmonics in the flux, and some of the flux will pass through some of the leakage flux will pass through the air gap, but some of the leakage flux will just circulate in the stator. And it's very hard to predict by using analytical model. So normally in this region, what we can do is only we simulate it by using finite element method. And next is the operating region, which which is the region that we are interested in, because this is the region that most of the induction machine, not most, every of the induction machine will running at. And the important point on this region is when the machine is running at close to no load speed, the rotor field is actually 90-degree lagging to the stator field. Because the real current in the rotor field is the dominant, but the magnetizing current in the stator is the dominant, so that's why there's a 90-degree lagging. However, when the load increase, the rotor field will very rapidly close to 180 degree of the stator. This is very important in calculating the UMP, because if the flux is 90 degree apart, then there is no flux cancellation, which will cause more UMP. And this is the UMP graph simulated by finite element analysis. The finite element that I use is in political magnets. So from here we can see that in the high slip region there's quite the UMP is quite high, and the UMP will drop after when there's lesser leakage flux, the UMP will drop. The reason that the leakage flux will cause more UMP for a cage rotor induction machine is because the high harmonics flux won't cut through the rotor bars, which the rotor couldn't generate a counter force to counter flux to cancel the UMP. And in this case, we can see that there is an increment of UMP near to the synchronous speed. So in this region, just now I mentioned, the stator field and the rotor field is actually 90 degree apart. That's why there's a sharp increment of the unbalanced magnetic force. And to have a better understanding on what is the slip that we should operate at, we should operate the induction machine at, so the UMP over torque ratio is introduced, which we can see from here. The minimum point is around 0.03 slip, so this is the point that if we operate at this point, the UMP will be at the lowest point. And yeah, okay, so a control method can be implemented. We can either use a scalar control method or vector control method. Vector control method, we need to know the information of the angle, and the scalar, and both of them we just need to get to know the voltage and the current from the stator, and we can estimate the unbalanced magnetic force, and from there we can find the slip, and from here we can choose the best flux that the induction machine can operate at. So this is quite easy controlling method. So the advantages of putting in the control according to the UMP over torque ratio that I mentioned just now is, obviously the UMP could be reduced, and this other than the UMP can be reduced, this also can reduce the losses. The losses that I reduce includes the mechanical losses, and also the losses from the power, because if a machine is not running at a full load torque, and we are using a full load flux, means that there is a lot of energy wasting. So there's also a lot of people suggesting that reducing fluxes to according to load to save the energy. And the disadvantages here is the slow response time of the machine, because by changing the flux, by changing the d-axis flux, the response time is very low, because the rotor time constant is quite low, quite high. Yeah. So, but this is not the case for a renewable energy generator, as the load will be quite constant, and I mean, if compared to 0.5 seconds, the load will be quite constant. So, and there's one more disadvantages is the strategy only applicable when the machine is not running at the full load, because this strategy is we just reduce the flux to reduce the UMP. That's why when the machine is running at full load, we can't really reduce the flux of the machine. However, for renewable energy generator, most of the time the machine won't be running at the full load. It's also quite good to reduce the UMP by reducing the flux. So after that, I do a finite element simulation, which I do an analytical calculation first, and I put in to the finite element simulation to check whether the force really can reduce or not. So from here, for constant load of 18 Newton meter, we can see that the load is constant throughout the sleep. So the load is constant. So from here we can see the UMP is actually just like what I show in the UMP over torque ratio. The lowest UMP is at 0.03. So actually for 18 Newton meter, probably the machine will be running at 0.2 or around here, this region. So we can see that the UMP can actually decrease by 50%. So this method is, you can show that you can reduce the UMP, and then this is the power loss model of a typical induction machine. And the point that I highlighted is the point that the machine actually operates at. So if we are putting in on the full load flux in a machine that without control, the machine will actually operate at this point. So in this point, the UMP will be quite high, and there is quite a lot of power loss. However, if we reduce the UMP, we can see that the power loss, we can also save the power loss, and other than that, we also can reduce the UMP of the machine, which is quite important to save the lifetime of the bearing. So the last slide, I'm going to say about why is it reducing a 50% UMP is very important. From here we can see the bearing lifetime versus the radial force of the bearing. So so we can see that if our machine has a 2000 Newton radial force, we will have around 80,000 hours of lifetime. However, if we can reduce from 2000 to 1500, we can actually increase the bearing lifetime by more than 60 to 70%. So this is quite attracting, because this not only can save the bearing lifetime, we also can reduce the power loss. So this is my presentation, and thank you.
This production is brought to you by the University of Edinburgh.